There we go. Okay, so let's, what do you guys get? So it gave you the mean, right? Which is really should be mu. What did you get for your mu?
1.34.
And it didn't give you a variance, did it? What did it give you instead? Standard deviation. Yeah. What was the standard deviation? 0.96. That's good. That seems good. Or 9.6. We'll do 9.6. Now, I need the variance. What's the symbol for variance? Sigma squared. If I have sigma, how do I get the sigma squared? You square it, right? This is this squared. So you take this and you square it. You square both sides, right? If I squared both sides, I'd get sigma squared over here. So this is 0.96 squared, which is what, 0.92? Great. Nice. So is the Vice President correct? He says that they have on average 3. Yeah, it seems like he's off a little bit. He might be right. It could be a bad sample. I don't know, but it seems like he's probably off a little bit. Okay. Possible.
So that's correct?
What? Oh, the bank president?
Yeah, the vice president correct?
Well, I don't know. It's hard to say. It doesn't seem like it, but maybe. Because, again, if I look at sort of my error, we kind of figure, well, I might be, the mean may not be, like, this is a sample. If this was the, if that's true, if this truly represents it, then no. If this is a true representation of everybody, then no. But this is just a sample that it could be. Does that make sense? Because you might be off a little bit. So you'd have to go maybe a standard deviation in either direction, or maybe 1.5 or 2 standard deviations in either direction to kind of give you a sense. But yeah, Angel.
So for this one, you're only like determining if he's right or wrong based on the mean, not by standard deviations.
Well, then that's the thing, is maybe you want to give him 1 standard deviation in either direction to kind of say, well, maybe it could be, maybe if this is a sample, that's the question, is this is a sample or not. If it's a sample, you might need to give him a couple standard deviations in either direction to see if, of error, right, due to the sampling thing. So we'll kind of talk about that a little bit, but if we want a couple of standard deviations in either way, then that would be, we would go from 1, so we'd go 1.34 plus 2 times 0.92, and we'd get 3.81618. So it'd be from 0 to 3.16. So maybe he's right. Does that make sense? So we might say, well, possibly. It's kind of right on that edge. I'm not going to worry about that too much this chapter. That's going to come up more in chapter 7, and we'll talk more about that stuff then when we're talking about samples, and we can be more specific about it.
Where did you get the 0.92 from?
Oh, sorry, 0.96. My bad. I grabbed it from the variance and not the standard deviation. 0.96. So 0.4, 0.2. Is that right?
Yeah.
Okay. So the answer would be maybe. It's possible. So as most people should have 0 to 3.25, 0.26. It's kind of hard to tell. I don't want to spend too much time on it because I don't want to confuse you guys with a lot of things at once. We're going to come up with this is going to come up more in chapter 7. But something to kind of just have in the back of your head for later. All right. Okay, so now we're going to get into the binomial distribution. Let's have a reader. How about Sonia? Go ahead.
A binomial experiment is a probability experiment that satisfies a specific one has a fixed number of trials. Each trial has only 2 outcomes.
You should be writing this down, right? It's on your notes.
The outcomes of each trial must be independent of each other, or the probability of success must remain the same for each trial.
Perfect, thank you. So let's take a look at these. We'll start with number 2 first. Each trial has only 2 outcomes. So for example, a trial might be flipping a coin. Does that have only 2 outcomes? Yeah, what are they? Heads or tails, great. Another one might be rolling a dice and getting a 4. Either I get a 4 or I don't get a 4. Right? So you can take something that has multiple outcomes and make them into a binomial by saying it's either a blank or it's not a blank. I roll a 4 or I don't roll a 4. We kind of did that a little bit less than chapter 4. I pick a marble, and it's either a white marble or it's not a white marble, right? So you can do it that way. Fixed number trials. Fixed number trials means you know when you're going to stop before you start. I know I'm going to draw 5 marbles, and that's it. Or I know I'm going to flip the coin 8 times, and that's it. So you know exactly how many times you're going to flip the coin, and that's how many times you're going to do it. Or whatever your trial is. Whatever thing you're going to do over and over again, you're only going to do it that many times. And it's already set before you even start. And the last 3 kind of go together. They have to be independent and the probability has to be the same. We call those IID, independent and identically distributed. Basically it means that the probabilities can't change from trial to trial. So if I flip a coin, what's probably I get heads? Probably I get heads, guys. Great. If I flip it again, does the probability stay the same or change? Stays the same. So those would be independent and identically distributed. Good? So I have a question to ask of all of you. Maybe if I get this to work. Ready, all right? Anika, go ahead and read.
If I put 10 marbles in a bag and they are right, then I draw a marble to see if it is right or not. I do not replace the marble and repeat the trial one more time. Is this
All right, so you have the 4 requirements written down, right? Go ahead and take a look at them. Decide probably look at your. Do I put them back? Oh no, you can't. I can't because you can't see both of them at the same time. So take a look at your 4 requirements and decide if fixed number of trials. Trial only has 2 possible outcomes, and then each trial is. So first of all, what are you doing over and over again? Picking a marble. So that's your trial. Picking a marble is your trial. So from there, try to figure out if it's binomial or not. Talk to your neighbors for 30 seconds. Go ahead. Armida, what do you have to say?
It's a reading in place.
Is it?
Yeah, not. So that's a no. And what if I draw
Yeah, we only. Yeah, it's biased.
All right, let's take a look. So first of all, the first thing, do I have a fixed number of trials? Am I only doing this a certain number of times and set? How many times am I doing it? Yeah, 4 plus 1. So 1 plus another 4, so 5 times altogether. So I'm drawing a marble 5 times. 1 time plus 4 more. Good? So that's good. It has a fixed end. Does each outcome have only 2 possibilities? Yeah, because I'm looking and seeing white or not white. Good? All right, so let's do that. And the last thing is are they the draws independent and identically distributed? So I draw a marble, I look at it, I do not replace it, put it in my pocket, and then I draw again. What's probably I draw a white marble, given that? Yeah, now there's only 9 marbles. The probability changes. Do you guys see what's going on? If I don't replace it, the probabilities are not the same anymore. So then it's not binomial. Because the probabilities change. Every time I draw a marble and don't replace it, I change the probabilities. Do you guys remember the deck of cards? Right? Do you guys remember that, the deck of cards? I had 5 cards, one's an ace. I can open the deck. This is not the rigged deck, this is the other deck. I have 5 cards, one's an ace. What's the probability that somebody draws an ace? 1 out of 5. If they don't replace it, does it probably change for the next person? Yes. If the only way it stays the same is if they replace the card. So without replacement, the probabilities are not independent, they change. So it's not binomial. Okay, how about the second one? Talk to your neighbors. What do you guys think? Yeah, so the second one is binomial. Is everybody good with this part?
Yes.
Okay. If I have 4 out of 10 white marbles, what's the probability I draw a white marble? 4 out of 10. If I put it back, and I draw again, it's still 4 out of 10. If I put it back. Here's some notation that you guys should write down. Jay, go ahead and read for us.
The notation for the binomial distribution. P is the
So that's little p. It's a small lowercase p. So it's little p or little p. One of my classes call it little p. Little p. Keep going.
Little p, probability of success for 1 trial. Little q, probability of failure for 1 trial. 1 minus p equals q.
You guys should write that down. You're going to need that if it's not written down already. Keep going.
N, the number of trials. X, the number of successes. And n trials.
Yep. So please note, if X is how many successes you have, you can always have 0 successes. Don't forget 0. People forget 0. 0 the hero. And then at most you can have all of them be successes. So you could have n successes. It's possible. So X is some number between 0 and n. If I do it 10 times, I could have 0 to 10 heads. Right? Any number in between. Who's ever heard of mind your P's and Q's? Okay, I don't know what that means, but I do know that P and Q go together. So P and Q, they're connected. So they have to add up to 1 or 100%. So P is your probability of success, Q is the rest of it. Right? So 60% chance of one, 40% chance of the other. You guys see what I'm saying? They have to add up to 1 or 100% P and Q. So remember, P and Q, they're buddies, tied together. So the difference between little p and we'll talk about the big P later is little p is just probability of success for one trial, one tiny trial. You're doing this trial over and over again a bunch of times, probability of success for just one of them. That's little p. That's why it's little p and not big P. It's little p because it's just for that one trial. Okay. Okay, so here's your formula. I strongly recommend this one. It's less complicated. And you guys have already proven to me you know how to calculate this. So now you can just use your calculators to do it. Do you want me to show you how to do that again?
Yes.
Okay. So, say I want 10 choose, or 8 choose 3. Do you guys want a second to write it down? I'll give you a minute to write this down. So, what it is big probability. So, probability of getting certain number of successes. So, the probability that I have 3 successes is I'm going to draw 10 times, the probability I get 3 of them to be successes. 10 choose 3 times little p, the probability of 1 success one time to the x power, times little q, the probability of failure for just that one trial, raised to the n minus x power. We'll talk about what those mean, or how to find them a little bit more in a second. First, I'll show you guys how to find NCR. So, say I want 8 choose 3. 8, I put in the 8 first. Everybody see that?
Yeah.
8 choose 3. Put in the 8 first, and then go to math, which is right here on the left side. Go to probability, PRB, and then see where it says NCR right there?
Yes.
That's the one you want. Go down to that and hit enter. Down to there, enter. And then I want 8 choose what? 3. Put in 3. Enter. Boom. Done. Way easier, right? So you've already shown me you know how to calculate it on an exam. You can just do this from now on. Again, put in your n first, and then go to math, probability, down to NCR. Enter, and then put in the x. 6 choose 2, for example. There you go. All right. Now, you might ask, well, where does this formula come from? I'm going to show you. We're going to look at a tree diagram, because that will help you understand it better. Okay, Anjali, go ahead and read.
Say a particular couple had 3 children with a 0.6 chance of having a girl and a 0.4 chance of having a boy.
The tree would look like this. Everybody on board with this? So, our first child could be a what? Boy or a girl. 40% chance of boy, 60% chance of girl. Say there's a particular couple, they have a 40% chance of having boys. No matter what they have, the second child will have, again, a 40% chance of boy, 60% chance of girl. Everybody with me so far?
Yes.
Then from each of those, again, 40% chance of boy, 60% chance of girl. Remember, we're doing these trees. It's a story. It goes along. So whatever happens, your first thing happens, oh, you had a girl. Then it goes on from here. You had a girl, and then what happened? You can't go back. Your tree goes along some story. So this person had a girl, then a boy, then a girl. This person had 3 girls. Everybody good with this part? How do we find the probabilities of this? 0.6, yeah, you multiply along the branches. Girl and boy and then a girl. 0.6 times 0.4 times 0.6, 2 0.6s and 1.4. You multiply. How do I get here? Girl, boy, boy. 0.6 times 0.4 times 0.4. 2 0.4s and a 0.6 being multiplied. Okay, so everybody's good with this part here? Yes? No? Do you guys need a minute to talk about it? Do you guys want 30 seconds? Talk to your neighbors, 30 seconds. Go ahead.
You get this stuff? Got it. I got it.
Okay, so let's go ahead and move on from that. So here, we have the probability of having exactly 2 boys. So then our success, I want exactly 2 boys, then our success would be a boy. So then what would little p be? You guys want to go back?
0.6.
What's probably, little p would be having a boy, success would be having a boy. So little p would be what?
0.4.
0.4. Good. Which means Q is 0.6, because those have to add up to 1 or 100%. Good, so then my failure in this case would be having a girl. I want to have 2 boys and 1 girl. I want to have 2 successes and 1 failure. Good? Everybody on board with that? So I need to have, so take a look at this. What's our N? N is how many times we do it? Well, we're going to pick a kid. How many times are we picking a kid? We're going to have 3 children. You guys don't go there. We're having 3 children. We adopt 3 children randomly. And how many times are we picking a child? 3. So our N's 3. Everybody on board with that part? X is, what's X stand for? Nope. Successes. How many successes do we want? 2. Yeah, we want 2 boys, 2 successes. What's N minus X then? N is 3, X is 2, 3 minus 2 is 1. What does 1 represent?
Low Q.
Kind of. It's little q would be my probability of this. So this would be my number of failures. Does that make sense? In this case, it would be the number of girls. Because these 2 things need to add up to n. Successes and failures better add up to my total. Yes? Okay. So you kind of think of it as my failures. So let's take a look at how this plays out. So exactly 2 boys, x equals 2, so all the ones in purple have exactly 2, maybe I'll circle them in purple. All the ones in purple have exactly 2 boys. Do you guys see that? Yes? What do they have in common?
1 failure.
They have 1 failure. They all have 1 failure and 2 successes. So what does that mean? They all have girl, boy, boy, 0.6 times 0.4 times 0.4. 2 0.4s and a 0.6 being multiplied. They all have that. Do you guys see that? They all have 2 boys, 2 0.4s being multiplied, and 1 girl, 1.6 being multiplied. Does everybody see what I'm saying? So how do I get, what's the probability of having exactly 2 boys? That, or that, or that. Is there, right? Ors we add. So I'd add these up. However, since they're exactly the same, I can just multiply by 3 because there's 3 of them. Right? Everybody see what I'm saying? If this was 10%, 10% plus 10% plus 10% is 30%, or I can just do 3 times 10%. Make it 30% because they're all exactly the same. So I just need to multiply by how many of them I have. So this part, let's take a look at this part here. Where does this come from? The point, this part here, comes from my p, probability of success, to the x power. I want 2 of them. Are you guys with me? That's this part of the formula right there. Then I also have the q to the n minus x. Q, that's 6, right? This is my q to the 1 power. Why 1? Because that's how many failures I have. That's my n minus x. Are you guys following that part there? And then I need, so that's this part, but I need 3 of them, right? Because I have 3 of them. I need to add these 3 amounts together, or it's multiplied by 3. So I need this times that times 3, because there's 3 of them. That will give me the problem that I'm looking for. Why 3? Because I have 3 children. Say I had these 3 children here. They are unborn embryos. And I'm God. I'm going to randomly pick 2 of them to be boys. How many ways can I choose 2 of them randomly to be boys? I can say, oh, you 2 are going to be boys, or you 2 are going to be boys, or you 2 are going to be boys. It's 3 items. I'm randomly going to choose 2 of them and assign them to be boys. You guys understand what I'm saying? Does order matter? No, I'm just going to pick 2 of them. So that's where this 3 choose 2 comes into. What's 3 choose 2? 3 times 2 divided by 2 times 1, 3. So this is the number of, let me find a color for it. This is the number of branches with 2 successes, 2 boys. Exactly 2 boys. So that's where this 3C2, or sorry, this is where the NCX comes in. Here's an example. Say I had 4 kids. They're probably getting exactly 2 boys. So all these here in orange, yellow, are the ways of getting exactly 2 boys. How many ways, here are my 4 children. I'm God. Here are 4 children. How many ways can I randomly pick 2 of them to be boys? These 2, or those 2, or those 2, or these 2, or those 2, or these 2. How many ways are there? 4 children. How many am I choosing? 2, right? I have 4 children. I'm randomly choosing 2. So 4 kids. Choose 2 of them. Do you guys remember how that went? 4 times 2, 4 times 3 divided by 2 times 1, right? So that's 12 over 2, which is 6. How many of them are there? 6. Does that make sense? So that n choose x tells me how many branches are going to have the result I want, are going to have 2 out of 4 boys. X out of n successes. And then I need to find the probability of this. So that would be 0.6 times 0.6 times 0.4 times 0.4. So 0.6 squared times 0.4 squared. Are you guys, is this making sense? Or are you guys all like, Kara, okay, you're right there, sort of? All right, fine. No worries. So this is where it comes from. Again, this part here tells you how many outcomes, how many branches end up with exactly X successes out of N trials. And then this is the probability of getting to that branch. In other words, the probability that I have X P's being multiplied and n minus x q's being multiplied as they go along the branches. Probably of having exactly x of them be x successes. So remember that probability, you multiply that. If I wanted 3 boys, it'd be 0.4 times 0.4 times 0.4. Right? How many of those you have? So the probability of getting to that branch. All right, so let's go ahead and try some stuff. Just to kind of remind you these, let's get someone to read them. Chris, go ahead and read.
N denotes the fixed number of trials, X denotes the specific number of successes in N trials, so X can be any whole number between 0 and N inclusive. P denotes the probability.
Little p.
Little p. Success
Little p.
denotes the probability of success in one of the little n trials. Little q denotes the probability of failure in one of the little n trials.
And this,
Probability.
big P, yep, keep going.
Probability of X denotes the probability of getting exactly X successes among the n trials.
Yep. So let's take a look at a problem. Survey of doctor visits. Ivana, go ahead.
The survey found that one out of 5 kids say he or she has visited a doctor recently. The 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last week. Y, R, D, X is the number of people in the paper who visited the doctor last week.
Great, so with your neighbors, try to figure out what's N, what's X, what's P. And it helps to kind of think about what happens over and over and over again. That's your trial. And then how many times you did that, that's going to be your N. X is the number of successes you want. P is the probability of success for just one trial. Why don't you take a minute and talk to your neighbors about that, see if you can figure those out.